Hello?
Huh?
Hello?
Hello? Hello?
Tell me.
Hello?
Hello? Tell me. Do you have any doubt?
Hello? Hello?
Hello? Hello? Hello? Good afternoon. Am I audible? Am I audible? Yes. Yesterday, we have completed the fifth method. The name of the fifth method is linear method. It is a method of finding the solution of first order and first degree. So we are in second part of the differential equation. The second part of the differential equation is ordinary differential equation. In the ordinary differential equation, we are in third subtopic, ODE. For ODE, first order and first degree. In the first order, first degree, we are discussing the methods of finding the solutions of first order and first degree differential equations. Actually, we have 6 methods. Out of 6, the 5 methods are completed. And also we have discussed about the last method, sixth method. The name of the sixth method is non-linear method or equations reducible to linear. Already we have seen how to convert the non-linear to linear and how to choose the transformation also. Now let us continue the last class, continuation of the last class. Method 6. The name of the method is non-linear method or equations reducible to linear differential equations. Non-linear method or equations reducible to linear. There are two types of first order non-linear differential equation. In the first order first degree, there are two types of first order non-linear which are reducible to linear. Out of two types, one of the non-linear is Bernoulli's equation. So first we read the Bernoulli's general form. a differential equation of the form dy by dx plus p of x into y equal to q of x into y power n. After this, within the brackets, since n not equal to 0, comma 1 is called a Bernoulli's differential equation, in short form BDE. In dependent variable y. If you replace y with x, x with y, that is if you interchange the variables, then that will be Bernoulli's in x. Note point number 1. The above Bernoulli's differential equation in variable y can be reduced to a linear differential equation in variable z by the transformation y power 1 minus n equal to z. Because of this y power n on right hand side, the equation is non-linear. To make it linear, we eliminate y power n on right hand side. To eliminate this y power n on right hand side, we divide both sides with the y power n. So on LHS side, in the second term, y by y power n becomes y power 1 minus n. And if we replace y power 1 minus n with some other variable z, and after simplification, we'll get a linear equation in new variable z on. That is why it is a transformation. Suppose if it is Bernoulli's in variable x, then the transformation will be x power 1 minus n equal to z on. This is one of the type of nonlinear for first order first degree, and this is called Bernoulli's differential equation. Same as linear only, except right hand side y power n term. Now we write the another type of first order nonlinear, which is reducible to linear on. We write this as note point number 2. A first order nonlinear differential equation of the form, first order nonlinear differential equation of the form f dash of y into dy by dx plus p of x into y, so p of x into f of y equal to q of x. Can be reduced to a linear differential equation in variable z by the transformation f of y equal to z. So this is another type of nonlinear differential equation which is reducible to linear only. This is another type of nonlinear. And for this transformation is f of y equal to z. According to linear differential equation, on right hand side we should have only function of x. Here also on right hand side we have only function of x, that is q of x. Before equal we should have the function of x, that is p of x, into some variable with the power 1. But here p of x into f of y is there. F of y means it is a function of dependent variable y. Because of the function of dependent variable, it is a non-linear differential equation. But it is also reducible to linear only. So one is Bernoulli's equation, other one is this node point 2 equation. Only these two are reducible to linear for first order first degree on. Let us do the problems on this. We are going to second page. I'm writing the problem. The solution of the differential equation y dash plus 3y by 2 equal to 3x into y power 1 by 3 whole divided by 2 is. On right hand side there is no derivative term. On left hand side in the second term there is no derivative. Only in the first term of the LHS part is containing the derivative only. That it is a first order with the power 1. So it is a first order first degree differential equation. We can check the variable, subvariable, condition, homogeneous condition, all this. But here directly we check whether it is linear, non-linear. Derivative power is 1. Next, here dependent variable is present, its power is 1. Other side, dependent variable is present, but its power is 1 by 3. So it is a non-linear. It is a first order non-linear. If it is a first order non-linear, we check whether this is in the form of Bernoulli's or not. The general form of Bernoulli is dy by dx plus p of x into y equal to q of x into y power n naught. We check whether all these terms present or not in the equation. First term is derivative. Here also we have the first term as derivative. This is present. Function of x into y present or not. Function of x is 3 by 2 into y. This term is present. On other side, function of x into y power n. Here, this is a function of x into y power n. All these terms are present in this equation. Therefore, the given equation is directly in Bernoulli's form only. So we can find the solution of this equation by converting non-linear to linear using the transformation. Let us do the problem. First, write the given equation. Given dy by dx plus 3 by 2 into y equal to 3x by 2 into y power 1 by 3. So this 1, it is in the form of dy by dx plus p of x into y equal to q of x into y power n naught. Now to make it linear, on right hand side, we should eliminate y power 1 by 3. For this, we divide both sides with y power 1 by 3 only, which implies 1 by y power 1 by 3 into dy by dx plus 3 by 2 into y divided by y power 1 by 3. That is y power 1 minus 1 by 3 on. That is y power 2 by 3 equal to 3x by 2 only. This is equation 2. According to linear, standard form of the linear, on right hand side we should have function of x. On right hand side we have a function of x only. Next, before equal, in the second term we should have the function of x into y power 1. But here function of x is 3 by 2 into y power 1. In place of 1 we have 2 by 3. So we should not have this term only, according to linear. We should have some variable with the power 1. That is why we are replacing this with some other variable with the power 1. That is a transformation. Let y power 2 by 3 equal to z. So this 3. When we introduce some new variable z like this, we have to change the dy by dx only. For this, we differentiate both sides with respect to x. Then 2 by 3 into y power 2 by 3 minus 1 into dy by dx equal to dz by dx. So this 4. So we replace these two terms, that is replace y power 2 by 3 with z. We replace the 1 by y power 3 dy by dx with dz by dx. Using 3 and 4, 2 becomes, that is when you substitute 3 and 4 in 2, that becomes like this. In place of y power 1 by 3 dy by dx, we are the, this 2 by 3 goes other side, that becomes 3 by 2 into dz by dx plus 3 by 2 into z equal to 3 by 2 into x. The equation 2 is becoming like this. In every term on both sides, we have common term 3 by 2 constant. We eliminate this. After elimination of this, the equation becomes dz by dx plus 1 into z equal to x. So this 5. This is the linear differential equation in variable z only. The given nonlinear is reduced to like this. We can convert the nonlinear to linear like this only. This is in the form of dy by dx plus function of x into y equal to function of x. But in place of y, we have some other variable z. Therefore, this is the linear differential equation in variable z. And to write the solution of this equation, first we try to find integrating factor. Here, integrating factor equal to e power integral of 1 dx equal to e power x. The general solution of phi is given by integrating factor z, dependent variable z into integrating factor e power x equal to integral of non-homogeneous part, that is q of x. Here q of x is x into integrating factor e power x dx plus c on, which implies z into e power x equal to integral of x into e power x. By using the integration by parts formula, its integral is x into e power x minus e power x plus c on. This is the solution of equation 5, but we require the solution of equation 1. Equation 5 is a equation in terms of two variables z and x. That is why its solution is in terms of x and z only. But we require the solution of equation 1 in terms of x and y. So replace z with our assumption y power 2 by 3 only. Therefore, y power 2 by 3 into e power x equal to x into e power x minus e power x plus c. Is a general solution of equation 1. Now, it is a method of converting the non-linear to linear and writing the solution by using linear method. This is one of the type of the first order non-linear, and its name is Bernoulli's equation. Except this y power n, other part is always linear one. Only because of y power n, this total equation becomes non-linear. Now we go to the next problem. Problem number 2. The solution of the differential equation tan y into dy by dx plus tan x equal to cos y into cos square x is solution of the equation is. It is a given differential equation. Whenever differential equation is given, first we should write the differential equation in one of the standard form of the differential equation. We have two general forms. One is dy by dx equal to f of x comma y. Other one is m dx plus n dy equal to 0. We try to write the equation in this form. Dy by dx equal to cos y into cos square x minus tan x divided by, don't write this, just listen this one. Again, we go back to the previous page and we do the problem. Now here I will like to tell you how to choose the method depending on the problem. Whenever the first order first degree is given, first order first degree differential equation is given, first we should write the differential equation in any one of the standard form. Now I am writing the derivative form. Cos y cos square x minus tan x divided by tan y. This is the one of the general form. Or we can write this as other way, like this. Cos y cos square x minus tan x dx plus minus tan y dy equal to 0. We can write any one. After writing the standard form, we verify all the methods conditions. With this, all the methods are completed only. Now we start from first method, variable separable. To apply variable separable method, in the function f of x comma y, the variables must be in the form of function of x into function of y. In the denominator, only function of y. In the numerator, we have both function of x and y, but we cannot separate here. So variables are not separable. We cannot solve this problem by first method. Next, you have to check the homogeneous function condition satisfies or not. That is, homogeneous method condition satisfies or not for this function. According to our homogeneous method, this function should be homogeneous function with the degree 0 only. Here all are transcendental functions. Tan y is a transcendental function. Cos y is a transcendental function. Cos square x is a transcendental function. Tan x is a transcendental function. For all these transcendental functions, inner functions are not homogeneous function with the degree 0. That is why this total function is not a homogeneous function. So second method is failed. Next, we verify the third method condition. According to third method, dou m by dou y must be same as dou n by dou x. This is m. This is n. M with respect to y equal to minus sin y cos square x, and n with respect to x equal to 0. These two are not same, so not exact. Whenever it is not exact, skip the non-exact method, directly go to the next method, because next methods are simple methods only. Suppose next method linear is not applicable, non-linear is not applicable, then we come back to the non-exact, last priority. So finally, we cannot solve this problem by variable subvariable. We cannot solve this problem by homogeneous method. We cannot solve this problem by exact method. Next, we check the whether it is in linear or not. The standard form of the linear is dy by dx plus function of x into y equal to function of x. It is a linear differential equation in variable y. If all these terms of the standard form present in the differential equation, then the given equation will be linear, otherwise not linear. But in the differential equation, we have transcendental functions of dependent variable y, transcendental function of dependent variable y. That is why it is a non-linear equation. If it is non-linear equation, for first order first degree, we have two types of non-linear. One is Bernoulli's, other one is other type of non-linear. So first we check whether this is in the form of Bernoulli's or not into y power n. According to standard form of the Bernoulli's equation, the differential equation should be in the form of like this. So we check for all these terms. Derivative is present. Function of x into variable y present or not, check it out. First of all, in this, there is no variable y. That is, the y is not present independently only. We should have y like this independently only. So this term is absent. This term is absent in the equation. And this term is also not present. So the given nonlinear is not in the form of this Bernoulli's equation. So we cannot solve this by Bernoulli. Next, we have other type of nonlinear. We check the given equation is in that form or not. Other form is f dash of y into dy by dx plus f of y into p of x equal to q of x. This is the another type of first order nonlinear. We check all these terms present or not. So the given equation is here, tan y dy by dx plus tan x equal to cos y into cos square x. It is the equation. If all these terms present in the equation, then we can convert the nonlinear to linear and we can solve the problem by linear method. Now we check for one by one. In the first term, if you observe the standard form, in the first on left hand side, the first term is function of y into derivative only. Here function of y into derivative present. Next, function of x into function of y. Here it is function of x into function of y is 1. It is also present. It is these two are present. Next, other side, function of x only. But here only, it is not only function of x. It is function of both x and y only. Not like this only. F dash of y dy by x plus f of y p of x equal to q of x. So on right hand side, we should have only function of x only. But before equal, we should have function of x into function of y. In this equation, on left hand side, in the second term, only function of x is there. Other side, function of x into function of y. So we interchange these two so that we get this form only. Tan y dy by dx plus minus cos y into cos square x equal to minus tan x. Now again, we check for all these terms. After equal, only function of x. Here also it is only function of x. Before equal, function of x into function of y. Function of x into function of y. This is also present. Next, function of x into derivative. Function of x into derivative. All these terms are present. But there is some condition. Whatever we have the quotient here, whatever we have the quotient of this derivative, this quotient should be derivative of this function. It should be derivative. This f dash of y should be derivative of this f of y only. This condition satisfies or not, we check it here. In place of f dash of y, we have tan y. In place of f of y, we have the minus cos y. But cos y derivative is not tan. So this condition is failed. Therefore, this is not in the form of this. Next, we rewrite the same equation other form. Instead of interchanging these two terms, we try to eliminate the cos y on other side. If we eliminate the cos y on right hand side, to eliminate cos y, we multiply both sides with the secant y because its reciprocal is secant. Secant y into tan y dy by dx plus secant y into tan x equal to cos square x. On right hand side only function of x, before equal function of x into function of y, and very first term is derivative into some function of y. This function of y is the derivative of this function. I want to check it on. Secant x derivative secant x into tan x. So secant y tan y is the derivative of this. This equation is in the form of this, and also the condition is satisfied. So we can convert this non-linear to linear. And after that, we can add the solution by linear method. Otherwise, we cannot convert and we cannot write the solution. So finally, we can find the solution of this by using linear indirectly on after conversion. So let us go back to the previous page and we solve this problem by method of. We are going back to previous page. Now let us do the problem. Directly, I'm multiplying both sides with secant y. I'm writing the equation here. Secant y into tan y into dy by dx plus secant y into tan x equal to cos square x. So this one. Since it is in the form of f dash of y dy by dx plus f of y into p of x equal to q of x. Now to convert this nonlinear to linear, in place of this secant y, we require this some function of, so there is some variable in place of this f of y, we require some variable with the power 1. That is why we are replacing the secant y with some variable power 1. Let secant y equal to z. So it's 2. Again, we are introducing some new variable. So let us change the dy by dx. For this, we differentiate both sides this with respect to x. Then secant y into tan y into dy by dx equal to dz by dx. We substitute these two in the given equation. Using 2 and 3, 1 becomes, in place of first term, we are writing the dz by dx. In the second term, in place of secant, we are writing the z into tan x equal to cos square x. So this is 4. So this is the linear differential equation in variable z. Conversion of non-linear to linear is completed. After conversion, we solve it by linear method. According to linear method, we require the integrating factor for writing the solution. Integrating factor equal to e power integral of tan x dx. E power integral of tan x is tan equal to sine by cos. So integral of tan x is log of secant x, which is equal to just secant x. The general solution of 4 is given by dependent variable z into integrating factor secant x equal to integral of cos square x into integrating factor secant x dx plus CR. On right hand side within the integral, one cos, one secant get cancelled. Cos remains, integral of cos is sine. On left hand side, in place of z, we write directly our assumption secant y. Therefore, secant y into secant x equal to integral of cos is sine plus c is a general solution of 1. So this is another type of nonlinear, and this type of nonlinear is reducible to linear by the transformation f of y equal to some z. In place of f of y in the given equation, we have secant y. That's why we are replacing secant y equal to, we are replacing secant y with a z only. After that, we can write the solution by linear method. It is the method of finding the solution. This is the second problem. So with this problem, all the 6 methods are completed for writing the solution of first order and first degree differential equation. So with this problem, all the methods are completed. With all these methods, the third part of ordinary differential equation. The third part of the ordinary differential equation is first order and first degree differential equation. We are in second subtopic of differential equation, or second part of the differential equation, ODE. In the ODE, there are 4 subtopics. Out of 4, the first one is solution, second one is types of solution, third one is first order, first degree, and next fourth one is second and higher order linear. So out of 4, 3 are completed only. Now at the end of all these methods, we'll discuss about the method of choosing the method depending on the problem. Or here I will show you how to choose the method depending on the problem. Or we write all the methods conditions together at one place. The general form of first order and first degree is, the general form of first order and first degree differential equation is dy by dx equal to f of x, it is in derivative form. Other form of this is m dx plus n dy equal to 0. These two are the general forms of first order, first degree. So in the examination, if you are given first order, first degree, first we check the variable separable method condition. The condition for this method is f of x comma y equal to function of x into function of y only. Like this, if we are able to separate variables in m, n, function f, then we can solve it by variable separable method. Suppose if it is not in separable form, then we check whether the function f is function of linear expression or not. F is a function of linear expression ax plus by plus c. Suppose h of x equal to g of y, directly we can solve this by variables. Suppose the function is like this, function of linear expression. Indirectly, we can find the solution by same method, by replacing ax plus by plus c equal to z only. It is the first method condition. Suppose this method condition fails, then we go to next method condition. Next method is homogeneous method. The condition for this is, if you take the first form, this function should be homogeneous function with the degree 0 only. Or if you take the second form, m and n should be same degree homogeneous functions. If it is homogeneous function with the degree 0, this function will be written as function of y by x. That is x power 0 into function of y by x. Or y power 0 into function of x by y. That is why we are replacing y by x with v, or x by y with v. So if these two methods condition fail, then we go to the third method, that is exact method. The condition for exact is dou m by dou y equal to dou n by dou x. Suppose this condition satisfies, so we stop here and we do the problem by exact method. Suppose this condition fails, then that will be non-exact differential equation. In the non-exact method, we have written the 5 methods for writing the integrating factors on it. When dou m by dou y not equal to dou n by dou x. In this, we have written the 5 methods. Whenever it is non-exact, first we observe the non-exact equation, whether this non-exact equation contains inspection type or not. Suppose for non-exact equation, if we have an inspection type like this, x dy plus y dx, then directly we come to the inspection method. And for this inspection type, the possible multipliers are 1 by 1, 1 by xy, 1 by xy power 2, 3, and so on in general, n. Other type of inspection is x dy minus y dx. For this inspection type, the possible multipliers are 1 by x square, 1 by y square, 1 by xy, comma 1 by x square plus y square, comma and so on. Next, other type of inspection is x dx plus y dy. For this inspection type, the possible multipliers are 1 by 1, 1 by x square plus y square, comma 1 by x square plus y square power 2, 3, 4 in general power n. Whenever the differential equation contains any one of these inspection type or any one of these 2 out of 3, then directly we come to the inspection. Otherwise, we skip this, we go to next one. Next, linear method. According to linear method, we have 2 general forms. One is dy by dx plus p of x into y equal to q of x. It is linear in y. Or suppose it is linear in x, then we write this as dx by dy plus p of y into x equal to q of y. So always it may not be linear in y. Sometimes it may be linear in x also. These 2 are general forms for linear. If it is non-linear, again we have 2 general forms. One is Bernoulli's dy by dx plus p of x into y equal to q of x into y power n. Other type of non-linear is f dash of y into dy by dx plus p of x into f of y equal to q of x. If you remember all these methods conditions, then easily we can identify the method depending on the problem. Just by looking at the problem, we verify all these conditions and then we go to the problem. So the method is not given in the examination. In general, method will not be given in the examination. Just the problem will be given like this. So find the solution or solution of the differential equation is done. So by looking at the problem, we can identify the method depending on the problem. If the first condition method satisfies, we stop there, we solve the problem by first method. Fails, we go to second method. Second condition satisfies, we stop there, we find the solution by second method. Suppose the first 2 methods condition fail, then we go to third method condition. Satisfies, we stop there, we find the solution by third method. Doesn't satisfy, instead of going for non-exact, directly we check the linear. If it is linear, we find the solution by linear method. Not linear, we try to convert the non-linear to linear. If it is in the form of these 2 on. Just remember all these, all the methods conditions together at one place. If you take a screenshot for this, Have you taken a screenshot? I think you have taken the screenshot. So with this third subtopic of ODE is completed. The third subtopic is first order, first degree only. Now remember one point at the end of the third subtopic. In the examination, dy by dx equal to f of x comma y is given, or mdx plus ndy is given. First, verify the variable subvariable method condition. Satisfies, find the solution by variable subvariable method. Doesn't satisfy, then directly check the exact method condition. The variable subvariable method condition satisfies, do the problem by variable subvariable. Doesn't satisfy, directly check the exact method condition. Satisfies, do the problem by exact method. Doesn't satisfy, directly check the linear method only. That's all. Because till now we have the gate questions on these three methods. And most of the questions were asked on variable separable method. Almost more than 95% question, more than 95% questions were given on variable separable method only. In the year 2018 for EC branch, one question was given on non-linear method. Otherwise, no question on that method only. And on homogeneous, no method. On non-exact also no method. No previous gate question. So till now we have the gate questions on variable, separable, exact, and linear. And there was only one question on non-linear method that was given in the year 2018 for EC branch only. So that is why the three methods are important. Out of three, the first one is very, very important. Keep it in mind. That's all. So, and these three are important. These three are simple. So don't worry about all the methods. And these three are simple. In easy way, we can check the conditions also. So with this, the first order, first degree is completed. Then we are going to last subtopic of OD, that is second higher order only. So far we have done all or with the first order, first degree only. Now we are going to higher order. In the higher order, according to our syllabus, we have only first linear equations only. In the higher order, we have only linear. But in the first order, first degree, we have both linear and non-linear. In the higher order, we have only linear. Let us write the fourth subtopic, the fourth one. Second and higher order linear differential equation. I am reminding one thing or note point for all. Whenever I say important, wherever I say important, that important is only for GATE, not for IES. For IES examination, till now we have only 4 years previous question papers. That is why we cannot say directly important just by going through these papers on. And for GATE examination, we have 28 years previous question papers. That is why I can say that so and so important by going all or by referring all the question papers on. I've gone through all these papers. That is why I'm saying that so and so important. So for IES, you have to prepare all. But most of the cases, these are the important only. Now, in the second higher order, first we read the higher order general form of the equation. By higher order general form of the differential equation. And then we read some other definitions. After that, we'll discuss about the method of finding the solution. In which the first bit, nth order linear differential equation. That is, we read the general form of the nth order equation. a differential equation of the form d power n y by dx power n plus p1 into d power n minus 1 y by dx power n minus 1 plus p2 into d power n minus 2 y by dx power n minus 2 plus and so on plus p n minus 1 dy by dx plus p n into y equal to q of x. Series 1. Comma, where P1, P2, and so on, Pn and Q of x are either functions of x or constants, comma, is called nth order linear differential equation in dependent variable y. In the first order first degree, that is in the previous part already you have written the like this general form of first order linear differential equation dy by dx plus py equal to q of x. It is a first order linear. If we add term by term, at the end we get the like this general nth order only. Some quotient here plus if I add the d square y by dx square with the power 1. Now it is a second order linear differential equation. Again, if I add one more term d cube y by dx cube, then it is a third order linear differential equation. If I add term by term like this, at the end we get the general order, that is nth order equation. Now in the higher order linear differential equation, instead of writing the higher order equation like this always with the derivatives, we try to write the same equation in simplest form. We try to write the same higher order equation in simplest form. Such a simplest form is operator form or symbolic form. Operator form or symbolic form. So next definition is operator form. Operator form or symbolic form of a differential equation. Just by using some notation, capital D for d by dx, we try to write this equation in simplest form. Such a simplest form is called operator form. If d by dx equal to capital D, if d by dx equal to capital D, comma d square by dx square equal to capital D square, and so on, d power n by dx power n equal to d power n in equation 1, then the equation 1 can be written as d power n y plus p1 into d power n minus 1 y plus p2 into d power n minus 2 y plus and so on plus pn minus 1 d y plus pn y equal to q of x. We simplify it. From each and every term y is common, d power n plus p1 into d power n minus 1 plus and so on plus pn minus 1 d plus pn into y equal to q of x. This is the operator form. Writing the differential equation in terms of d notation. And also we write this in short form, which implies f of d y equal to q of x, where f of d equal to d power n plus p1 into d power n minus 1 plus and so on pn minus 1 d plus pn. It is a polynomial in differential operator d, just like a naught plus a1 x plus a2 x square and so on plus a n xn, and n belongs to capital N only. This form is the polynomial function in variable x only, or polynomial expression in x. Like that, f of d is the polynomial in terms of d, just like polynomial in terms of x variable. In place of x, here we have the operator d by dx. Here, f of d y equal to q of x. The short form of this operator form. F of dy equal to q of x is called an operator form of a differential equation. Just studying the higher order linear differential equation in terms of d notation is the operator form. And this f of dy equal to q of x is the short form of this operator form. We are going to next page. The next page we have the third one. The first one is nth order equation. Second one is its operator form. Next, third one is auxiliary equation, in short form A dot E, or characteristic equation. Of a differential equation. If f of d y equal to q of x is a non-homogeneous linear differential equation. In the first part of the differential equation, is basic definition. In the basic definitions, we have seen the 8 definitions. Now we require all 8 definitions here onwards. We require all the definitions. We should know the linear, non-linear, homogeneous, non-homogeneous, order, degree, like this on all definitions. Now here in f of d y equal to q of x, we are going back to previous page. See the general form of the linear differential equation or nth order equation. On left hand side, every term is containing either a dependent variable y or its derivatives. And right hand side, the term is present q of x. It is free from x, free from variable y or free from derivative sum. Left hand side, every term is contained with the derivatives and a dependent variable. Right hand side, there is one term q of x without y, without derivatives. Because of this q of x on right hand side, this is a non-homogeneous differential equation. Suppose q of x is absent, then homogeneous. When q of x is 0, every term will contain either y or derivatives only. That is why homogeneous. Suppose q of x presents, then there will be one term without x, without a dependent variable y, without its derivatives only. Again, we are going back to next page. So f of dy is homogeneous part, q of x is non-homogeneous part. Totally, this equation is non-homogeneous equation. Right? So is a non-homogeneous linear differential equation in variable y. Then the algebraic equation f of m equal to 0 of this within the bracket, since d by m in f of d. That is, we can obtain f of m from f of d by replacing d by m only. Is called auxiliary equation of a differential equation. Later, I will give the example also, or by taking an example, discuss about this auxiliary equation also. It is about auxiliary equation or characteristic equation. Next, fourth one. General form of a general solution of non-homogeneous linear differential equation. General form of a general solution of non-homogeneous linear differential equation. If f of d y equal to q of x is a non-homogeneous linear differential equation in y, instead of writing the in variable y, just add the in y on, then its general solution is written as y equal to y suffix c plus y suffix p, where y suffix c is called a complementary function, CF in short form, and y suffix p is called a particular integral. In short form, pi. For a non-homogeneous equation, the solution will be written in the form of sum of two parts or sum of two terms. One term is yc, other term is yp, or one part is yc, other part is yp. So we try to write always the solution as a sum of two parts, yc and yp. Yc is the complementary function, yp is the particular integral. Here I will show you the reason for writing the sum of two terms or sum of two parts of the solution. The next page. Don't write, just look at this. dy by dx minus y equal to 0. Other side, dy by dx minus y equal to e power x. Look at both equations up. Are these two first order or higher order? Both are first order. Next, Both are linear or not? Both are linear or not? Yes. Both are linear because in every term we have a power of y as 1, power of derivative is 1, and there is no product of y its derivative, there is no transcendental function of dependent variable. So both are linear. Both are linear and that too first order. Then what is the difference between these two? Linear, first order. What is the difference? Very good. One is homogeneous, one is non-homogeneous. Now, if you observe the first one, dy by dx minus y equals 0, it is a homogeneous equation because all terms are with the derivative and dependent variable y. There is no term without these two, y and dy by dx. That is why it is a homogeneous. In other equation, there is one term without dependent variable y, without derivative on. This is free from, the rounded one is free from both y and derivative. That is why it is a non-homogeneous part and the total equation is non-homogeneous equation. This is a homogeneous part, this is a non-homogeneous part. The total equation is non-homogeneous equation. This is a linear homogeneous equation, this is the linear non-homogeneous equation. Already we know the method of finding the solution of the linear. First, we require the integrating factor e power integral of minus 1 dx, that is e power minus x. And for this integrating factor is also same, e power minus x. And to write the general solution, we write the dependent variable into integrating factor e power minus x into, that is equal to integral of non-homogeneous part q of x 0 into integrating factor e power minus x dx plus c. These are also y into e power minus x inside the integral non-homogeneous part q of x e power x into integrating factor e power minus x dx plus c. Y into e power minus x, this product is 0, integral of 0 is 0 plus c. Y into e power minus x, the product is 1, integral of 1 is x plus c. It is a solution. Or if you want to write the y in terms of other terms, we eliminate the e power minus x. For this, we multiply both sides with the e power x. 0 into e power x plus c into e power x, y equal to x into e power x plus c into e power x. And this part is 0. Y equal to c e power x plus 0. Y equal to c e power x plus x into e power x. This is a solution of this equation. It is a solution of this equation. Both are linear first order and one is homogeneous, other one is non-homogeneous. Now observe their solutions and tell me the difference between their solutions. There is one difference between their solutions. Just we can type, by typing you can tell your answer. I will see the in question answers tab. Now the difference between these two is one is homogeneous, other one is homogeneous. One is homogeneous equation, other one is non-homogeneous equation. And there is some difference between their solutions. Just observe the both. In both solutions, left hand side, same term, y, equal. On right hand side, first part is same, c e power x, c e power x. The main difference is between these two only. 0, not a 0. It is a difference. Except these two terms, other terms are same. Y same, equal same, c e power x is same. Here, why we are getting 0? Because of the 0, 0, 0, 0 in the non-homogeneous part. Here we are not getting 0 because of the function. That's all. So in the non-homogeneous part, if we have a function, correspond to that function, here we get some function here. We have some function, exponential sign or anything for a particular function, here we are getting some particular function. In place of non-homogeneous part q of x, if it is 0, then we get 0 here only. It is the main observation. So from these two solutions, we say that other part, c e power x is coming from this homogeneous part. This is coming from this homogeneous part, and this part is coming from non-homogeneous part. This is coming from non-homogeneous part. That is why we are dividing the solution into two parts. We are dividing the solution into two parts. One part is YC, other part is YB. Here, depending on particular function in the non-homogeneous part, we are getting one function here. It is a particular solution, particular integral. Then other part is called complementary function. So whenever the higher order linear equation is given, first you have to check whether the equation is homogeneous or non-homogeneous. Depending on that, we write the solution. If it is homogeneous equation, the solution will be y equal to yc, because q of x is 0, yp is 0. This yp is 0, only yc on. Suppose if it is non-homogeneous equation, then we should find both yc and yp only. So we can obtain the yc from homogeneous part, and we can obtain the yp from non-homogeneous part. Just remember it. It is the reason for writing the sum of the two terms in the solution for higher order linear. Right? Now we are going back to previous page. Here we have the note point. Note point 1. F of d y equal to 0. For this, general solution is y equal to yc. And second one, f of d y equal to q of x. For this non-homogeneous equation, the general solution will be y equal to yc plus yp only. So whenever higher order is given, first you have to check the equation is homogeneous or not. Homogeneous, only solution will be yc. And the non-homogeneous means yc plus yp is the general solution. Just remember this part. Okay. Now we are going to next one. Next page. Next, fifth bit. Wronskian of functions. Wronskian of functions. In which the first bit, if y1 dash and y2 dash exist, for y1 of x and y2 of x, then the Wronskian of two functions y1 of x and y2 of x is denoted by capital W of this within the brackets y1 comma y2 and defined as second order determinant. Second order determinant. Within the second order determinant, along the first row, the same functions y1, y2. Along the second row, y1, y2 first order derivatives, y1 dash, y2 dash. Therefore, W of y1 comma y2 equal to y1, y2, y1 dash, y2 dash. This is for two functions. Similarly, for any number of functions, we can add this. Now we add the three functions. If y1 double dash, y2 double dash, and y3 double dash exist for y1 of x, comma y2 of x, and y3 of x, then the Wronskian of three functions y1 of x, y2 of x, and y3 of x is given by w of y1 comma y2 comma y3 equal to third order determinant. Only two functions second order determinant, and three functions third order determinant, four functions fourth order determinant, and so on. Because of third order, along the first row, the same functions y1, y2, y3, y1, y2, y3. Along the second row, y1 dash, y2 dash, y3 dash. Along the last row, second order derivatives, y1 double dash, y2 double dash, y3 double dash. It is for three functions. Now we write two note points on this Wronskian. We write it on next page. Note point number 1. If w of y1 comma y2 equal to second order determinant y1, y2, y1 dash, y2 dash not equal to 0, then the two functions y1 of x and y2 of x are linearly independent functions. That is, we cannot express one function in terms of other one. We cannot write the one in terms of other one. There is no relation between these two functions. Independent means both will be different. That is independent. No relation between the two functions. Next, note point 2. If w of y1 comma y2 equal to second order determinant y1, y2, y1 dash, y2 dash equal to 0, then the two functions y1 of x and y2 of x are linearly dependent functions. So determinant is 0, that is Wronskian is 0. The two functions will be linearly dependent. Means we can express one in terms of other one, or one depends on other function. Independent, no relation. Depend means relation exists between the two functions. This Wronskian is useful to check the functions are linearly independent or not. So to check the independence or dependence of the functions, we require the Wronskian. In the linear algebra, we discuss about the linearly independence or dependence of the vectors. Like that here, independence and dependence of the functions. Because based on this, we write the solution of the differential equation for linear equations. So up to here, all the important points or definitions are submitted. Now next, I will explain the method of finding the solution of the differential equation for higher order linear. We are going to next page. Just stop writing, just look at this. Don't write, just look at this only. By taking the simple order equation for higher order, first I will show you how to find the solution of a differential equation. Here I will show you how to find a solution of differential equation by actual method. But we never follow this actual method. We follow step-by-step procedure only. So here I will show you how to find the solution by actual method by taking the simple order equation for higher order. Simple order means second order. Y double dash minus 5y dash plus 6y equal to 0. In this differential equation, highest order derivative is second order, so it is a second order equation. In every term, either y or its a derivative present, therefore it is a homogeneous equation. And also the power of the dependent variable is 1, the powers of the derivatives are 1. So this equation is linear, there is no product of y its derivatives. Next, its degree is 1 because highest order derivative is second order, the power of the second order derivative is 1. It is a second order linear homogeneous differential equation. Second order linear homogeneous differential equation with a degree 1. All the definitions are covered. So that is why we should remember all the definitions on. It is a second order linear homogeneous differential equation, independent variable y. Okay. Now here our aim is finding the solution of this equation. We are in ordinary differential equation. If it is ordinary differential equation, its solution is a relation between the variables. One of the variable must be independent, other variable must be dependent. So solution is a relation between the variables, that is y equal to f of x. It is a solution on. So our aim is finding the solution of this equation. Now I am taking the y equal to 0, that is f of x is 0 only. We check y equal to 0 is a solution of this equation or not. To check y equal to 0 is a solution or not, we check the LHS equal to RHS or not. For LHS, we require the y dash, y double dash. From this y, we write the y dash, y double dash. And if you substitute the LHS, if you substitute all this in the LHS, in place of y double dash 0, in place of y dash 0, in place of y also 0. This is equal to 0. Anyhow, RHS is 0. Here, these two same. So the differential equation is satisfied with y equal to 0. Therefore, y equal to 0 is a solution. Y equal to 0 is a solution of the differential equation. Right? And this solution is called zero solution or trivial solution. This is called zero solution or trivial solution. Just like linear algebra topic. In the linear algebra, one of the subtopic is system of linear equation. The system of linear equation, you will find the two types of equations. One is ax equal to b, other one is ax equal to o. This is non-homogeneous equation system. This is a homogeneous system only. For this non-homogeneous system, solution may or may not exist. Either may be one or many solutions. Like that here, for every homogeneous system, solution always exists, and the solution may be one or many only. And this one solution is called zero solution or trivial solution of the homogeneous system. Just like that here, for this homogeneous differential equation, y equal to 0 is always a solution. And this is called zero solution or trivial solution. Here, we are not interested to find zero solution. Our aim is finding the non-zero solution of the equation. But to find a solution that should not be zero. That is a non-zero solution. now come back to this. Our aim is finding the non-zero solution. To find the non-zero solution, we assume the y equal to some function as a solution. We take the y equal to some function as a solution. With the help of that, we try to find the actual solution of the equation. But our aim is finding the non-zero solution. So to choose one function as a solution of the equation, that chosen function should be non-zero only. Whatever you choose a function, that should not become zero at any value of x. That is a condition. So we have many elementary functions. Elementary functions are two types. One is transcendental, other one is algebraic. Again, algebraic means polynomial also, non-polynomial. So we have polynomial, algebraic, transcendental function. All these together are called elementary functions only. Suppose if I take the y equal to polynomial function, that will become zero for some values of x. So we never choose polynomial function. Next, if you take algebraic function, that also will become zero some values of x. So we never choose that. Next, log. Log is also zero at x equal to 1. So log 1 is 0. We cannot choose this. And if you take the sine is also 0 for n pi. Cos is 0, 2n plus 1 into pi by 2. And tan is 0. Like this, almost all functions will be 0 except one function. Except means that function is here exponential. Out of all elementary functions, only this exponential function never be 0 for any finite value of x. That is why to find the non-zero solution of the differential equation, we assume the y equal to e power something as a solution of this equation. And with the help of that, we try to find the actual solution of it. So here I will show you that part. Here I am taking the y equal to e power m into x as a solution of this equation. When I assume this as a solution of the differential equation, the differential equation will satisfy with this only. So I will substitute y dash, y double dash in this. For y dash, this becomes m e power mx, y double dash m square e power mx. If I substitute all this in the equation becomes m square into e power mx minus 5 into e power mx into m plus 6 into e power mx equal to 0. From every term, e power mx is common into m square minus 5m plus 6 equal to 0. So product of two terms is 0 here. Exponential into this equal to 0 means any one is 0, 0, both are 0 also 0, but exponential never be 0 according to our assumption. Or exponential never be 0, already we know that. So this should be 0 only. It is this equal to 0 means it is a quadratic equation. This will give two values for m equal to 2 and m equal to 3. These are the roots of the equation. Here we have taken y equal to e power mx, y equal to e power mx as a solution with unknown coefficient m. For that unknown coefficient, we got two values, 2 and 3 only. So corresponding to our solution will be like this: y1 equal to e power m1, in place of m1 2x, and y2 equal to corresponding to m2 value 3, e power m2x, that is 3x. So these two are non-zero solutions of this differential equation. It is an actual method of finding the solution. For this second order equation, we got two solutions, two non-zero solutions. Suppose if it is third order equation, if we do in this way, we get the third order equation here, and we get three roots. With the three roots, we get the three solutions. Fourth order equation, 4 roots, 4 solutions. In general, nth order linear differential equation, nth order algebraic equation, n roots. With n roots here, we write the n solutions only. So from this, we can say that nth order linear differential equation will have n solutions. Second order will have 2 solutions only. That is 2 non-zero solutions. Every solution is a function. We check whether these two functions linearly independent or linearly dependent only. to check the linearly dependent or independent, we require the Ranskin because here these two are functions. So to check the independence or dependence of the functions, we require the Ranskin. To check the independence of two functions, we consider second order determinant. W of e power 2x, comma e power 3x equal to second order. Along the first row, same functions, e power 2x, e power 3x. Along the second row, their derivatives, 2 e power 2x, 3 e power 3x. If we do the cross multiplication, that is product of diagonal minus product of non-diagonal, 3 e power 5x minus 2 e power 5x, that is e power 5x. Again, output is exponential. This is not equal to 0 for all x. So Ranskin is not equal to 0 means the two functions are linearly independent. Here the functions are solutions. So y1, y2 are two linearly independent solutions of the differential equation. So the second order linear differential equation has two linearly independent solutions. When the solutions are linearly independent, we can add the one more solution by taking the linear combination of these two only. K1 into y1 plus K2 into y2. It is a linear combination of two independent solutions. That is K1 into e power 2x plus K2 into e power 3x. K1, K2 are constants. This is the linear combination of two solutions only. This linear combination is also one of the solutions of this equation. Second order equation has two linearly independent solutions, and the linear combination of these two independent solutions is also one solution. And this solution is called complementary function CF or YC. Already I told you that for homogeneous equation, general solution is just YC. For a non-homogeneous equation, general solution is YC plus YP. Because of this homogeneous equation, this complementary function is the general solution. This is the actual method of finding the solution of any higher order linear differential equation. And also observe the solution, general solution. The solution is in terms of exponential. You take any linear differential equation, the solution will be written in terms of exponential. The reason for this is finding the non-zero solution on that. For every higher order linear solution will be written in terms of exponential, because to get the non-zero solution. But we never do every problem in this way. We never do every problem in this way. We try to follow the step-by-step procedure, right? So for the differential equation, we do like this only. For a given equation, first we write this equation directly. For a given equation of any order, we write this equation. This equation is called auxiliary equation or characteristic equation. That is the third definition. Already we have written the just now third definition. That is, I think we can find this in page number 5. Auxiliary equation or characteristic equation of a differential equation, right? So for a differential equation, we write the auxiliary equation and we solve it for roots. Depending on the roots, directly we write this linear combination. That's all. We follow this step by step only. Given equation, auxiliary equation, find the roots, and then write the linear combination. That is our solution. We never do all these things because of the higher order linear. In this higher order linear, we have only linear equation. For every linear equation, the solutions are always linearly independent. That is its a linear combination is also one solution. We need not to check all the solutions are independent, not always. So second order equation will have two linearly independent solutions. It's a linear combination, is complementary function. Third order linear equation will have three linearly independent solutions. Their combination is also one solution, that is complementary function. In general, nth order linear differential equation will have n linearly independent solutions, and their linear combination is one solution. That solution is called complementary function or YC, right? It is a method of finding a solution. Now we never do every problem in this way. Just we follow the step-by-step procedure and we follow that procedure on that, right? So we are going to next page. In this page, we write the the method of finding the solution of homogeneous equation. That is, we write the procedure. Method of finding the general solution of homogeneous linear differential equation. We write the step-by-step procedure. To write this procedure, we take the fifth order equation only. Particular order equation, fifth order. Let f of d y equal to 0. Say this one be the fifth order homogeneous linear differential equation with constant quotients. Fifth order homogeneous linear differential equation in y with constant coefficients. In the higher order, we have only linear, but for linear, we have two types of coefficients equation. One is constant coefficients, other one is variable coefficients. So let us start with the first constant coefficients. Step number 1. Express the given differential equation in operator form when it is not in the form of operator form. It is the first step. That is, always the equation may not be given in terms of denotation. The equation may be given in terms of like this: y double dash plus 4y dash plus y equal to 0, or d square y by dx square plus 4 dy by dx plus y equal to like this only. The equation is given like this. We try to write the equations in operator form, that is in denotation only. If it is already in denotation, no problem. Not in denotation, we try to write the equation in denotation. That is the first step only. Next, step number 2. Write the auxiliary equation. Auxiliary equation. In short form, A dot E f of m equal to 0. Since d by m in f of d. This is the second step. Third step. Solve f of m equal to 0 for roots m1, m2, m3, m4, and m5. After solving the roots, if you observe the roots, these roots may be real or complex. These may be real or complex. Real, again, these may be non-repeated or repeated or surds. That is a plus or minus root of b form. Complex. that is A plus or minus IB form. That's roots may be real or complex. All the roots may be repeated, non-repeated. Depending on the roots, we are at the linear combination. Step number 4. Here we have taken only fifth order equation. That is why we are getting 5 roots only. To write the procedure only, we have taken fifth order. Otherwise, we can take any order. In the fourth step, the first bit, if M1, M2, M3, M4, and M5 are non-repeated real roots, then we write the linear combination like this: yc equal to c1 into some constant into exponential, some constant exponential like that. Here constants may be a, b, c, d, k1, k2, k3, or c1, c2, c3, anything you can take. Now I'm taking the c1, c2, c3 as constants. C1 into e power m1x plus C2 into e power m2x plus C3 into e power m3x plus C4 into e power m4x plus C5 into e power m5x. When all the roots are different, then we have the linear combination like this. 5 independent solutions. The linear combination of 5 independent solutions is the complementary function, that is YC. Suppose some roots are repeated, then we write that in next case. Same fourth step, second bit. If M1, M2, M3 are repeated real roots and M4, M5 are non-repeated real roots, then YC equal to now corresponding to first 3 repeated real roots, we write the linear combination like this: C1 plus C2x plus C3x square into e power m1 equal to m2 equal to m3 only. Any one we can write. I am writing the m1x plus corresponding to other 2 repeated non-repeated roots: C4 e power m4x plus C5 e power m5x. Corresponding to 3 repeated roots m1, m2, m3, we have written the linear combination like this. Suppose 2 are repeated, just we write the C1 plus C2x e power m1x. 4 are repeated, C1 plus C2x plus C3x square plus C4x cube into e power m1. All 5 are repeated, C1 plus C2x plus C3x square plus C4x cube plus C5x power 4 into e power m1x, like this. Next will be third sum, that is third bit. In the same fourth step, we read the third bit. Correspond to non-repeated, we have written the linear combination. Correspond to repeated, we have written the linear combination. Now we read the corresponding to surds, pair of conjugate surds. After that, we read the complex roots. Third bit. If m1 equal to a plus root of b, comma m2 equal to a minus root of b, or pair of conjugate surds, and M3, M4, and M5 are non-repeated real roots, then Yc equal to M3, M4, M5 are non-repeated real roots. A plus root of B, A minus root of B are also real, but pair of conjugate surds. First of all five are non-repeated. So we can write the linear combination of 5 independent solutions of it. Like first one, C1 e power A plus B, that is A plus root of B, x, plus C2 into e power A minus root of B into x, plus corresponding to other 3 roots, C3 into e power M3x plus C4 into e power M4x plus C5 into e power M5x. Like this we can write it. Because all 5 roots are non-repeated, so we have written the linear combination of 5 independent solutions. And here we can write the first 2 terms in terms of other functions also. I will show you how to write this in the next page. So we are going to next page. Again, we come back to this page. Okay? Already we know that cos hyperbolic function cos hx equal to e power x plus e power minus x by 2 sin hx equal to e power x minus e power minus x by 2. Like this, cos h root b x equal to cos h root b x equal to e power root b x plus e power minus root b x divided by 2. Next, sin h root b x equal to e power plus root b x minus e power minus root b x divided by 2. If we add both sin and cos, the negative powers will get cancelled. We get the positive power terms with 2 times. So this becomes e power root b x equal to cos h root b x plus sin h root b x. Right? E power root b x. If we add both, we are getting like this. Suppose if we subtract both, we get the negative power terms. E power minus under root b x equal to cos h root b x minus sin h root b x. Subtract like this. This minus this. And if we multiply first one, both sides with the C1, 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 here C2, C2, C2. Again, if I add these 2 on both sides, corresponding sides, C1 e power root b x plus C2 into e power minus root b x on right hand side. From these two, C1, C2 is common here, C1, C2 common. That is C1 plus C2 into cos hyperbolic plus C1 plus C2 equal to sin hyperbolic. So here minus cos minus, this is minus. You are subtracting. So in place of C1 plus C2, we are writing this some other constant A or capital C1. I'm writing A into cos h root b x plus in place of c1 minus c2, writing the another constant b sin h root b x. This is c1 plus c2 and this is c1 minus c2. That is, if you go back to the previous page, c1 e power root a plus root of bx plus c2 e power a minus root bx. From the first two terms, e power ax is common. If you take the e power ax outside, inside, c1 e power plus root bx, c2 e power minus root bx. That is same as this. So we can replace this with the hyperbolic functions. That is why we write this in other form. Or yc equal to e power ax is common. In place of other terms, we write the some constant a. Instead of a, here I am writing the c1 again, capital C1, cos h root b, or I am writing the a on capital A, cos h root b x plus capital B into sin h root b x plus c3 into e power m3x plus c4 into e power m4x plus c5 into e power m5x. Both are same. Whenever the roots are pair of conjugate sets, we can write the solution in terms of exponential or in terms of hyperbolic functions. Any one we can write. And next, other case is pair of conjugate complex only. The fourth bit, if m1 equal to a plus ib, comma m2 equal to a minus ib, or pair of conjugate complex roots, and m3, m4, m5 are non-repeated, real roots, then yc equal to c1 into e power a plus ib into x plus c2 into e power minus a minus ib into x plus c3 into e power m3x plus c4 into e power m4x plus c5 into e power m5x. Linear combination of 5 independent solutions. So like previous case, hyperbolic functions for pair of conjugate sets. Here we can have a pair of complex in terms of trigonometric functions. I'll show you how to write this. You go to the 11th page. In that way, I will show you how to write. According to Euler's theorem, e power I theta equal to cos theta plus I sin theta, and e power minus I theta equal to cos theta minus I sin theta. Using this, we can add the same exponential functions in terms of trigonometry. Yc equal to e power ax is common. Instead of c1 e power ibx plus c2 e power minus ibx, we are the trigonometric functions because e power ibx is cos bx plus I sin bx only. E power minus ibx is cos bx minus I sin bx only. And after simplification, we can have the like this. Some constant c1 plus I b in place of the capital A cos bx plus some other constant b into sin bx plus c3 e power m3x plus c4 e power m4x plus c5 e power m5x. Like this, we write the linear combination of independent solutions depending on the roots. With the 4 different types of roots, we are writing the 4 different forms. Up here, 4 steps are completed. 4 steps are completed. Next, using this YC, we write the general solution. Step number 5. Step number 5. Write the general solution, the general solution of 1 as y equal to yc plus, sorry, only yc homogeneous. Write the general solution of 1 as y equal to yc. That's it. It is the procedure order. So for a given equation, first we write the operator form when it is not in operator form. Next, we consider auxiliary equation and we solve it for roots. Depending on the roots, we write the one of the linear combination. That is a complementary function or general solution of the homogeneous equation. Even though it is non-homogeneous also, the same method is required for non-homogeneous for writing the YC complementary function. And here, telling one point here, remember, keep it in mind. In the first order, first degree, out of 6 methods, 3 methods are important. What are 3 important? Variable separable, exact, and linear. Out of 3, which one is more important? Variable separable. Like that. In the higher order linear, homogeneous is very, 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 very important. From the higher order, most of the questions only from higher order homogeneous on. In the hierarchy equation, most of the questions were given on the homogeneous only. And this is very simple, easy only. Just writing the auxiliary equation, solving roots, choosing the answer. That's all, depending on the roots. So whatever we have important, which are simple, that's all. Remember that point. Whatever we have important, which are simple. Okay, the procedure is completed. Now, what is the time now? 3:57. Okay, we do one problem on this. Okay, we do one problem on this according to step-by-step procedure. The general solution of d square y by dx square minus 6 into dy by dx plus 9y equal to 0 is zero. It is a 2020 gate question of EC branch and is a 1 mark question. In the year 2020, 2 questions were given from the differential equation topic. Out of 2 questions, already we have done one of the question, that is from first order, first degree, that to variable subvariable. We have done that problem in the variable subvariable. That question was given for 2 marks. And this question was asked for 1 mark. It is a 1 mark question, and it is a higher order equation. Options were given, but I am not writing the options here. 2020 1 mark question of EC branch. Now let us do this problem step by step procedure to know the procedure. This differential equation is given in terms of derivatives. It is not in the form of operator form. And we try to write the operator form when it is not given in operator form. For writing the operator form, we replace d with the, that is, we replace the d by dx with the d square by dx square with the d square on. Okay. Let us do this problem in the solution. First, we have the given problem. Given d square y by dx square minus 6 into dy by dx. After doing this problem, we stop the session. We'll have a break after this. Plus 9y equal to 0. So this is 1. It is not in operator form. To write this in operator form, we replace d by dx by capital D, d square by dx square by d square, right? Which implies here d square y minus 6 dy plus 9y equal to 0, which implies d square minus 6d plus 9 into y equal to 0. It is the operator form. Writing the given equation in terms of d notation is the operator form. Or we write this in simplest form or in short form, f of dy equal to 0, comma, where f of d equal to d square minus 6d plus 9. (6d plus 9). So writing the differential equation in operator form is completed. Up to here, first step. Next, second step, we write the auxiliary equation. Consider auxiliary equation f of m equal to 0. We write the f of m from f of d by replacing d by m. M square minus 6m plus 9 equal to 0. Now it is auxiliary equation, that it is one algebraic equation in terms of variable m, and we solve it for roots. Now we can tell the roots. M equal to 3, 3. The roots are real but repeated. The roots are real but repeated on, which implies yc equal to c1 plus c2x into e power 3x. Or we can have the c1 e power 3x plus c2 into x into e power 3x. Both are same. Therefore, the general solution of 1 is y equal to yc. That is y equal to c1 plus c2x into e power 3x. That's it. It is a method. But in the examination, don't do all these things. In the examination, we do like this only. For this problem, options will be given. So from the differential equation, directly write the auxiliary equation. In place of second derivative, write the m square. In place of first derivative, write the m. In place of y, write the 1. In place of y1, in place of first derivative m, in place of second derivative m square. Write the auxiliary equation, solve it for us, choose the answer directly. We never do all these things on examination. Just write the auxiliary equation, find the roots, and choose the answer. That's all. Here I have done like this. I have done this problem with each and every step to understand the procedure only. In 5 steps, we can do this problem. That is, here to here is 1 step, writing the equation in terms of denotation. And this is 2nd step, writing the auxiliary equation. And solving it for roots is a 3rd step. Depending the roots, writing the auxiliary equation is the 4th step. And using the YC, we write the general solution. This is the 5th step. In 5 steps, we can do the problem. In 5 steps, we can do the problem. But in the examination, we never do like this all these steps. Just write the auxiliary equation, solve it for roots. Based on roots, choose the answer directly. That's it. So with this, I close this session. We continue this session in the next class. So after this, you can take break. Anybody has doubts, can stay and you can ask your doubts. So we start the doubt session and we continue the doubt session up to 4:30. Hello.
Hello, sir.
Hello. Tell me what.
Sir, we take non-zero solution as e power mx, na, sir, y equal to.
Yeah.
Sir, at minus infinity, e power minus infinity is 0, na, sir.
Now we consider the real number system. In the real number system, means r equal to open interval minus infinity comma plus infinity. That's all.
Oh, okay, sir.
Right. Next. Hello.
Sir.
You can ask your.
Hello.
Hello. Tell me.
Sir, I have a doubt in number 8F.
8F.
In number 8F. Yes, sir.
What is your doubt here?
Sir, here you told that. If the order of the equation is n, then it will have n number of.
Linearly independent solutions.
Hello.
N
linearly independent. So, sir, the last. Then linearly independent solution. Okay, sir. Okay. So, suppose we have a 5th order equation.
6th order.
5th order.
Okay.
Suppose. Then, sir, means there will be 5 linearly independent solutions.
Only 6 linearly independent solutions. 6th order means 6 linearly independent solutions.
For 5th. Okay, sir. Then their linear combinations means different combinations. Can they be the solutions of the equation?
The main equation will have 6 linearly independent solutions, but the 6 linear independent solution depends on the roots only, based on roots. All 6 are different. We write the first form. Suppose some are repeated, we write the second form. Thirds are there, third form. Based on that roots.
Yes, sir. That one we got. Sir, I am telling that out of 6, if we take 4 or 3 and we represent it as a combination, then will it be a solution of the given equation?
Repeat it.
Sir, suppose there are 6 linear independent solutions, and out of that, take 3 or 4 and represent it as a combination of this K1 like this. Will that be a solution of the given equation?
Out of 6, how many are?
Less 4 or 3 means all the 6.
4 are repeated. You are saying that.
Sir, sir, for complementary function, we are representing as a combination of all the linear equations. Yes or no, sir?
Yes.
So that out of 6, if we take 4 out of that and we represent it
No. We should take
something,
6 only. We should
then
not only just 4. We should take all 6.
okay, if all 6 with it, then it will be a complementary function. And
Right.
okay, sir, okay.
With the 4, we cannot write down.
Okay, so it will be a combination of all the
6 linearly
independent equations.
Right. With all 6 linearly independent combination, we can generate infinitely many solutions for different values of C. Got it?
Okay, sir. And sir,
Tell
here
me.
I am having doubt that if some complementary solutions, complementary function only, we will generate all the particular solutions, no, sir?
Yeah.
Then what are those nearly independent solutions? Not, I am not able to, means I am having confusion.
Do you have a confusion between particular solution, complementary function, or what is your actual confusion?
No, sir. Particular solution will come from complementary function, no, sir?
Yeah. Correct. Actually, we read the 2 types
Then
of.
what are those?
No. In 2 ways, we read the particular integral, particular solution. This particular integral is also particular solution because integral is a solution only.
Okay,
If we write any solution from the general solution, particular values, that is also one particular solution. If it is non-homogeneous equation based on non-homogeneous part, if you write the one solution, that is also particular solution. Is it clear?
Okay, sir.
Uh,
Okay, sir. Got it.
we are going to next person. Hello.
Audible, sir?
Good afternoon. Can I ask you?
Sir, in Bernoulli equation, you said
Uh.
n cannot be equals to 0 and 1.
Yeah.
Right?
Uh,
If we place n is equals to 1, then how to solve that equation, sir?
variables are variable directly. I'll show you.
But is it possible to solve or
Wait. I will show you. dy by dx plus p of x into y equal to q of x into y power n equal to 1. Right?
Right.
And these 2 terms are having some common term y. dy by dx equal to.
Okay, got
Right? Variables
Right.
are variable. That's it.
right. Sir, there is one equation d square y by dx square
Okay.
plus y by dx plus 6 is equals to e raised to minus x. Is this equation linear?
Tell me. D square y by dx square, dy by dx plus 6 or just a 6
Is equals to e raised to minus x.
e power minus x.
Right.
Okay. Is it your equation?
Yeah. Is this linear, sir?
Yeah. Linear. It is linear. Because
But sir,
power of the derivatives is 1. There is no product of dependent variable. It's a derivative. Also, it is transcendental function. It is a function of independent variable. So it is a linear equation.
okay. We are not supposed to take coefficient of 6, na, sir?
No. We send this to other side only. We send
Okay,
this other side. That is a q of x. Y term is absent here because last term in the general form Pn y equal to q of x. Pn quotient is constant. This term will be absent only. So just we have only 2 terms.
Okay. Got it. Thank you, sir.
Hello.
Hello, good afternoon, sir.
Good afternoon. Tell me what.
Sir, I had a doubt. Means like you gave an equation, no? Y double dash minus 5y dash plus 6y equals to 0.
Let me write first. Tell me. Y double dash.
Sir, you only Y double dash minus 5y dash.
plus 6y equal to 0. Okay.
Sir, here you found the roots as 2 and 3, and
Ah.
then you checked Wronski. They were linearly independent. But if it is linearly dependent, then means how the answer will change?
If it is linearly independent, then only we write the linear combination. That will be the complementary solution. If it is linearly dependent, we cannot write the linear combination, and we cannot write the complementary function.
Okay, sir. Means like if linearly independent, then
Then only we can
complementary
write
function
linear
cannot be written.
That is why we can write the linear combination.
Okay, sir. Okay, okay. That was the doubt. Okay, okay. Thank you, sir.
Next, hello.
Sir, mine is done, sir.
Hello.
Over. Okay.
Yes, sir.
Hello.
Uh-huh.
Hello. Yes, sir.
Tell me your doubt.
Sir, I maybe a silly one, but I had doubt about the linear dependency. How can I know the y1 or y2 were linearly dependent or independent?
If you want to check the independence or dependence, we consider Wronskian.
So,
If you want to check the linearly independent or dependent, we consider Wronskian, depending on number of functions. Okay. That Wronskian is defined as determinant. If two functions were
Yes, sir.
there, we find the determinant. Determinant is not equal to 0, independent. Determinant is 0, we can say dependent. Got it? Hello?
hello.
Got it? You?
Completion is probably mind of problem. Okay. Okay, sir, I'm putting it.
Your doubt is completed?
Hello.
Hello? Hello? Am I audible?
Yes, sir.
What is your doubt? You ask your doubt.
I'm sorry. There's a network problem in my phone.
Okay, no problem.
Okay, we'll ask this, sir. Thank you.
Hello? 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 Anybody there? Hello? 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 Do you have any doubt? Okay, no one is asking any doubt. So I'm closing this session, note session also.